All right, welcome back to differential equations this evening. So today we're going to talk a little bit about 3.1 and 3.2, and I'm going to do this in two different videos, maybe three, to kind of show what's going on here. Okay, so the linear models, these are nice. Okay, we like linear models. Pretty much linear models, we have a y prime plus some kind of a p of x, y is equal to f of x or q of x. Some of these will be first order linear where you use an integration factor, okay? A lot of these, actually, you don't have to work that hard. You could use separable, okay? Now, occasionally you might have to deal with some kind of a weird, a weird substitution where you might have an ax plus by plus c kind of a thing. There are other substitutions that we could have. Okay, we're not going to be dealing with binomial or Bernoulli rather too much because that has a y, right? That's f of x times y to an n, which is now not linear, so it doesn't really work. But generally, this is the kind of format you're going to be seeing. And this is actually like one of the more complicated formats that you're going to be seeing for linear models. So case in point, okay, we talk about the two topics I'm going to break this down to is the first one's going to be more of a population type of a model, and I'll follow that through to its logical conclusion. And then the next one I'll do is a mixing problem, and then maybe the third one is some miscellaneous problems, maybe some resistors or some circuits. Okay. So we talked a little bit about this in chapter 1, and it's really the vocabulary. It's something you have to get used to. Where they're going to say something clever like the growth or the change in population. Okay, let's do this so I can write a little bit more clearly. The change in population is, what do they say, is proportional to the population. Okay, so that's they're going to be their problem. It's going to say the change in the population is proportional to the population. Okay, or yeah. So we could do something clever like dp by dt or p tick, right, is proportional. Okay, there's my constant of proportionality times p. Okay, if you're an old school person, you may have written this one first, but I don't think any of the textbooks do this anymore. So, okay, it kind of looks like an ant head that was kind of severed, something, or an alpha that's like a little bit weird to write. But that was the proportionality symbol. And the first thing that we did, even old school, is the first thing you do is you replace this thing with an equal sign and you say constant of proportionality. And then we have to go ahead and solve this differential equation. Okay, so technically it is, right, the same format that we have up here, because we could do something clever like dp by dt minus kp is equal to 0, and now we're back to what we have. But like I said, I mean, you can use an integration factor here if you want to. You don't have to. Like, this is separable. Let's choose that route, okay? So, making logical sense, if we have a change in population is proportional to the population, if you have a small number of bunnies, you're going to make a small number of new bunnies. If you have a large number of bunnies, you're going to make a lot more bunnies every time they get together. Okay, so that's pretty much my example as we're just talking about bunnies. Okay, because everybody knows what they do. Okay, so say we have an initial population, right, the rabbits, and in 1 year's time, so we're going to start with p sub 0 bunnies. Okay, and in 1 year, okay, we're going to have 120% of the initial. Okay, now all we're doing is we're just seeing what the growth is we could be more explicit about what we're modeling, and maybe we could just do like a birth rate, and we could subtract a death rate, and we could have like how many do we lose to predators, how many do we lose to old age, all that kind of stuff. But generally, like this we start with this many, right, and we have 120% of the original later. Okay, in 1 year we have 120%. That pretty much accounts for all of that stuff. So it's kind of wrapping all of that, jumping all of that into like one number. Okay. So yeah, what we're going to just do is we're going to say, well, dp by dt is equal to kp. Let's go ahead and solve this, right? It's not, this will be the nicest answer, the nicest question I ever give you, right? And then all we have to do is say natural log of p, right, is equal to, okay, we have kt plus c. We note that we're talking about population, which is always going to be positive. So even though we could be more precise, put in our absolute values, we know that population is going to be positive, so we don't really need to work with that too much. And then we have to solve for p, so what we're going to do is we're going to logify both of these things. Okay, take the anti-log, raise both sides, make both sides the exponent to the same base. Okay, technical terms, the anti-log. So we have p is equal to e to the kt plus c, and then we're going to say this is equal to e to the kt times e to the c, and this is, I will pause this for a moment. I don't know what that was about, but whatever. So we have c e to the kt. All right, so that's our model. And if you recall from college algebra, you probably had 3 different formulas, right? You had it for population growth. This is the same formula for continuous interest. All right, and it was radioactive decay. Okay, and they pretty much all come from the same starting point. The amount of stuff, animals, money, whatever, is the rate of change for that stuff is proportional to the amount of that stuff. Okay, now in radioactive decay, it's getting smaller. In species that are going extinct, it's getting smaller. We don't have negative interest yet, and hopefully we never will, but you know, it can happen there too. Okay, the amount of interest, the amount you lose money based off of the amount that you have. Okay, that would mean that people are charging you to store your money. Okay, that the banks wouldn't give you interest. You would pay them to store it. Okay, so that's what that would look like. But here we have, yeah, we have our solution. We did a great job, right? We have P is equal to CE, right? CE to the KT. We're told at time equals 0 that we had an initial value. Okay, P was equal to P naught. So P equals C e to the 0. C e to the 0 is 1. So we just have P is equal to P naught rather. P naught is equal to C. Okay. So our formula so far, P, I promise it gets harder. Okay, there we go. Now you need the next piece of information. So we started with, right, this was the starting condition. And what else did we get told? We get told that, well, in 1 year, there's 120% of the original bunnies. So when t equals 1, right, we have 1.2 of the original, right, 120%, equals P naught e to the k, and then t was 1. Okay, so those cancel. So we pretty much have natural log of 1.2 is equal to k, right? We go through and do all of this. This is natural log of e to the k. Either way you do this, I usually bring this down in front, right, with the logarithm rules, times natural log of e, knowing that natural log of e is 1. So we get K is equal to the natural log of 1.2, and we can figure that out a bit. Okay. So that's our, that's our problem. We might further ask, okay, when will the population triple in size? Okay. So we can say something like we have 3p0, right? That's triple the size, that's p, is equal to my initial p0, e to our k. I'm going to go ahead and put a little subscript on that so that I don't have to write out a long number. And we'll just say my bunnies here. Hold on. It's incredible. She's got nothing to say until I want to record. Okay. So when will the population triple in size? So we replace the population with 3 times the initial. And then we're just going to go ahead and solve this. Okay. So we have natural log of 3 is equal to the natural log of e to the population, right, the growth constant for the bunnies. Natural log of 3. Oh, there's a t here. T. Okay. Both of these things are going to come down, so we have kb times t times the natural log of e, which is 1. And then we're going to say t is equal to the natural log of 3 over, right? What was kb? Kb was natural log of 1.2. Now we're just going to evaluate this. Okay, I'm going to go get my calculator. I'm going to be right back. So let's go ahead and figure out what our t is. And our t is going to be the natural log of 3 divided by the natural log of 1.2. Okay. Equals, and we get it to about 6 years. Okay, a little bit more. Okay, so there's our solution for this. Now, you might rightly ask the question, like, well, does this, why, what happens if, like, can there be too many bunnies? Like, yeah, there can be. This is called exponential growth. Okay, this is the exponential growth model. And the assumption we're making is that the things in your environment will never run out of room, will never run out of food, and will just continuously expand forever and ever and ever, and we'll never have a problem. And while we might like to think that's the case for our planet, that's not really the case. At some point, there will be not enough room. Okay. So what do we do? Okay. Well, what we're going to do is we're going to add in another condition. Okay, and here it goes from linear to nonlinear. Okay, so what we're going to say is the rate of change is proportional to the product of the amount there, the number of animals there, there, and the difference in carrying capacity. That's the maximum amount of things that can exist there without bad things happening. The difference in the carrying capacity and the population. Okay. I'm sure the book will put it a little bit better poetically here. Okay. So we have the proportional to the product of, well, dp by dt, right, is equal to k, that's our constant of proportionality, times p, and what we want to have here is the difference of the carrying capacity and the population. Now, The example we're going to do, I'm going to put some numbers on it because otherwise we're going to be running into some alphabet soup here. Usually your carrying capacity is a C, right, or an A. So I guess we could, I'm going to call it R for rabbits, okay, minus P, okay. And then we could solve this one, okay. So right now, this is now a nonlinear equation, right, because what we have is K R P minus a KP squared, nonlinear, okay. So we could do this with Bernoulli equation now, right? Or we could just divide by everything that has p's in it, right? And then do partial fractions because it's still separable. And when you're working these problems, like honestly, if it's separable, that's the one you want to go with first, because as horrible as the integrations might be, like the weirder techniques that you're going to learn are just going to make things worse. Okay, separable. If you have the option of keeping it separable, chances are you want to keep it separable. Okay. So I tried this a couple of times here, and I'll be honest, this was not a good example to do because there was a lot of letters. It's like I don't want to do the letters T just yet. That's a secret trick, by the way. If you are working, if you're going to be going and taking more engineering classes, I remember several problems where it was an easy problem, except here's what they did. They said thickness, we're trying to do like how thick does the rubber on the bottom of a cup have to be to hold this stuff in it or something, right? Thickness is just T, solve in terms of T. And it turned a problem where like a student who would normally get a C in the class, right, they could solve that problem. A student who's getting a C could solve this problem if it was listed as like, 0.25 centimeters or something. You put a T in there, and it wipes out the C-level students. It completely destroys them. Even B-level students, it completely wiped out. The only students that get this are A-level students now. And we just took away the 0.25 and we made it a T. So if you can practice problems where they, take away a number from you and use it in symbols instead, that's something you should definitely practice. If it helps you to like, well, what if it's pi thickness? What if it's pi centimeters? Right. Well, now you have a symbol that means both a symbol and a number for you at the same time. So it might be easier to kind of ease yourself into it. But you should definitely practice problems that don't give you all the numbers. Like maybe they have a force A or something, and you have to solve in terms of A. Right. And you're solving everything else. Like, when does it break? Right. And then you have this A sitting here, and you might have to have two unknowns or something to the parameter. Okay, what are we going to do? So let's come up with a problem. Let's say we have, let's make it easy. Start with initial population of 100 bunnies. Okay, and we have a carrying capacity of 500 bunnies. Okay, so we just imagine this big meadow that is kind of constrained. So maybe there's a river on one side, and river wraps around, and we've got this field with all the bunnies, very big field with little bunnies, and maybe we've got an interstate over here. Okay, so the bunnies are kind of constrained between the river and the highway, so they can't leave. Okay. So we're just going to see like how big this gets. This is a lot easier with like goldfish in a pond, right? Because the pond is already self-contained. But that's what we're looking at. Okay, and we'll still say the same thing, right? In 1 year, okay, there'll be 120 bunnies. Okay, so let's go ahead and set this thing up because now we have some numbers to put in here. Okay, so we're going to do the same thing. We're going to say, well, this is dp by dt, right, is equal to, I still don't know what my constant of proportionality is, right, p, okay, but we have this 500 minus p here, Okay, and that's really going to make things easier. Again, rather than dealing with all the letters we could throw into this. Okay, so dp over, right, p 500 minus p, and that is equal to k, okay, dt. So we have to integrate both sides. Partial fractions, right? So let's go ahead and do a sidebar and deal with our partial fractions. It's not really going to be that bad. So we have, I'm going to replace this with 1 because we're not going to, right, we could factor out the dp for a moment. Okay, so we'll just have our 1 over p, 500 minus p is equal to a over p plus b over 500 minus p. Okay, so that's going to be a 500 minus p plus bp is equal to 1. All right, so let's see here. We've got 500a is equal to 1, and we have minus a p plus bp, not pb, okay, bp is equal to, how many p's we got on this side? None. I think it's pretty much to say that, it's safe to say that negative a plus b equals 0 means that a will equal b, okay, and a from this statement here is 1 over 500. Okay, not so bad. Okay, so let's go ahead and set this up. So we've got 1 over 500 times 1 over p plus 1 over 500 times 1 over 500 minus p. These all have a dp on them because we're going to integrate, and this is equal to k dt. Okay, integrate both sides, right? And this is 1 over 500 natural log of p plus, now look what happens here. Okay, now if you need to do this, that's fine. Okay, we could set u equals to 500 minus p, du equals negative dp. Okay, so there's really a negative sign in here, so we're going to go ahead and account for that. Okay, and say this is going to be a minus. Okay, that's going to be a minus 1 over 500, or this natural log, sorry, 1 over natural log, ln 500 minus p is equal to kt plus c. Okay. Let me warn you in advance, there's going to be a couple of algebraic steps here. It's all going to be delightful. Okay, so here we have this. We have 1 over 500 times the natural log, okay, and this is p over 500 minus p. Remember, there's a logarithm property that says that log of a over b is equal to log of a minus the log of b. We just did this in reverse. Okay, and that's equal to kt plus c. Multiply both sides by 500, so we have natural log p over 500 minus p is equal to 500 kt plus, I'm still just going to call it c. Okay, you can keep the 500 there, but honestly, it's just c. Why are you keeping the 500 here with the k? Some things might drop out, and I want to kind of track where this is going to be going. The reason why I'm not keeping it here, this is why, because we're going to logify now. Okay, so this is going to be p over 500 minus p is equal to e to the 500 kt times, right, times here, times on the bottom, plus up in the exponent, times on the base. Okay, e to the c, which is just going to be a constant. So I really don't want to track e to the 500 c and have to deal with all of that. So we're just going to call this c. So we have p over 500 minus p is equal to c e to the 500 kt. Okay. So now, okay, we get to do some fun stuff with this. So we're going to say this is P is equal to 500 minus P times CE to the 500 KT. So now we're going to have a 500C. So P is equal to 500 CE to the 500 KT minus P C E to the 500 KT. So I told you the algebra here is going to be delightful. So here we have P plus P C E to the 500 KT. That is equal to 500 C E to the 500 KT. Okay. Factor out a P. Okay, so we get 1 plus CE to the 500 KT is equal to this thing. This doesn't change. Okay, let's go ahead and divide. You think like, oh, I know where this is going. I assure you, you don't. Okay. You love to do this. All right, so there we go. Now we have one more step. What we're going to do is we're going to multiply top and bottom by 1 over C e to the negative 500 KT. 1 over C e to the negative 500 KT. So why are you doing that? It's okay, because this is what we're going to have. Like, what happened to 500? It's going to stay there. The C's cancel, the E's cancel. So we just end up with a 500 because we want the carrying capacity to be on top. Okay. This business here, right? 1 over C e to the negative, that's just 1, isn't it? And then we have plus 1 over C e to the negative 500 KT. Okay. So before we do anything else here, all right, I just want you to realize, like, when t goes off to infinity, right, as t goes to infinity, what is this term looking like? This term is looking like 0, right? E to the negative 500 KT goes to 0. So 1 over C times this thing, still 0. So as t goes off to infinity, we get P is equal to the carrying capacity. That's why they do all of this stuff, to kind of, this horrible algebraic stuff, is to make answering this question, what happens when t goes to infinity, an easier question to answer. You say, well, that was not easy. I'm like, yeah, but you're the engineer and you're the one who has to suffer doing all the calculations. You're going to let the biologist who doesn't take differential equations have an easier time of figuring out what's going on here. Okay, so it falls to us to kind of shoulder the burden of all of this. Okay. All right. So that's our first step here. Okay. The rest of this now is, it's not, you know, I think the rest of this is actually a college algebra problem. We'll continue with this because it's not the easiest thing in the world. But when t is equal to 0, right, the first, how many bunnies did we have? P was equal to 100, right? So what do we have? We have 100 is equal to 500, and then this is 1 plus 1 over C, right? So this is going to be 100. Actually, this is going to be 1 plus 1 over C, right? Is going, we're cross multiplying. So I'm divided by the 100. This is equal to 5 now. Okay. Because I'm going to divide both sides by 100 as I'm multiplying through here. So this comes up, this comes down. Okay. So we have 1 over C is equal to 4, subtracting 1 from both sides. Okay. And then I think we could safely say C is equal to 4. Okay. So, yeah. So this is P is equal to, or 1 over C is equal to 4, with C is equal to 1/4. Okay. But 1 over C, we don't have to do that. 1 over C is equal to 4. So our formula here, 500, 1 plus 4 e to the negative 500 kt. Look at that. Okay. Again, trust me, I did this with the alphabet soup in it, and that was not a pleasant experience trying to keep track of C's and A's. And I mean, when we did the partial fraction, I had two more letters in there. It got to be a little, this is getting to be too much. Okay, so I just didn't do any of that. Let's see, what else do we want to ask? Do we want to ask anything else? What was this? I was asking in 1 year, because we still have to figure out what K is. So in 1 year, we had P was equal to 120. Okay, so still we have the same business we have to go through. And this is a college algebra problem. Okay, maybe pre-calc. Okay, but I would not think twice about giving my pre-calc people this problem to do of saying solve for K. Okay, I would not lose any sleep at all telling, oh, that's a 1 now, telling them to solve for K here. Okay, so again, we have 1 plus 4e to the negative 500k is equal to 500 over 120. Okay. How do you guys want to do this? Do you want the numbers, or do we want to? I didn't have numbers. I didn't have a calculator. I worked it out before, so it looked a little bit less fun. Okay, let's just do this. Okay, so we've got 1 plus 4e to the negative 500k is equal to 50 over 12. Let's cast out a 2, so we've got 25 over 6, 5 sixths. Subtract 1, subtract 1. So we've got 4e to the negative 500k. We've got 25 over 6 minus 6 over 6. What is that, 19 sixths? 4e to the negative 500k. So divide both sides by 4. E to the negative 500k is equal to 19 over 24ths. When I take my logarithm of both sides, (19 over 24 is a number that's less than 1. So when I take this logarithm, it's going to be negative. All right, because remember, logarithm looks something like this. Here's 1. So anything that's a fraction is going to give me a negative number. So it's going to be negative. So when I divide both sides by negative 500, right, we're going to get negative 500k equals whatever this mess is. And we get k is equal to negative 1 over 500, ln 19 over 24, and that's pretty much what she just wrote there. Okay, so what is that going to be? Negative 1, oops, negative 1 over 500, okay, times natural log of 19 over 24, and we just get a small number, okay, 4.67 times 10 to the negative 4th. Okay, and now we have all the parameters set up. If there's anything else we need to solve, that's not going to be too bad to do this, okay? I'd probably keep this one as a letter because it's cumbersome to write. Right, there's my bunnies. Okay. I'm not going to go through the next little part, but you could rightfully ask, like, well, what if we take a certain amount out or add a certain amount in? Okay. So how do we account for it? Like, what if we wanted to add bunnies to this field? Maybe we have hunters or something. Or what if we built a little rabbit bridge across our freeway so that they could escape, right? Or we built one across the river so that they could leave, and we wanted to track emigration, and we counted them. So what we would do, right, is we would say this is K, P, okay, and then again our carrying capacity minus P. Again, most people use an A here or C, and then plus or minus some H, right? This is a number added or subtracted to the population. Okay, so maybe you dealt with this and you artificially came in and you were going to, grab 30 bunnies per year to give to people for, don't give people bunnies for Easter. Okay, but whatever you would want to do with them, or maybe you want to add in like 3 rabbits a year, just in case. Okay, but you would do that, and then we would solve this. Okay, and what would this look like? Well, this would look like KRP, right, minus KP squared plus or minus H is equal to dP dt. But let me rearrange this. Okay, so that's going to be, let's call negative K is equal to little a. So we'd have the A P squared plus KRP, or KR, right, is equal to B plus BP, right, plus or minus H is equal to dP by dt. And then we could divide by this, and we'd have all the fun of completing the square, right, and having that integration come by. Okay, so it's still separable. Okay, this is getting less and less appetizing. I would really rather not do something like this, but it is a solvable problem. I don't think the book actually does this to you. The homework problems don't do this to you, so I'm not going to do it either. But that's, if we wanted to artificially add or subtract something, that's how we would do it. Okay, so what I'm going to do is stop the video here, because I think we know everything we would ever want to know about bunnies at this point. And but that's how you deal with population problems. Okay, so if you just have exponential growth, right, KP, and then you wanted to add or subtract some, we could do that. And again, we would just divide this whole thing. Okay, and that's how that would work. Again, keep it separable, keep it easy. So the hardest thing, interpreting their words into the equation. We're going to do some examples out of the books shortly. Like that'll be the 3rd video, I think. So we can get some practice doing that. But that's how you deal with this one. Okay, so I'm going to go ahead and stop, and then we'll do mixture problems in the next video.